All right, so welcome to this session. This has been fascinating to hear all of these talks. My name is Karen Daniels, and my title is actually a lot more than I'm going to talk about because, in fact, I'm a physicist who works on the property of materials and have um, been thinking a lot about how my work on granular materials relates to NASA's science and exploration missions, and particularly how that might relate to things like extraction, processing, handling, drilling, anchoring, all those things. So if we can go to the next slide. Um, I'm a physicist, right? Not a space scientist, not a planetary scientist, not an expert in exploration. So why do we want to do physics research on granular materials in this context, right? And as a physicist, I would say that our ability to perform experiments in a wide range of environments really is going to create new science. What new phenomena happen when we are in environments beyond the ones we experience on Earth, right? And so both low gravity and vacuum and plasma environments, right, are unusual here on Earth, but are very common in space. And so really probably very cool new phase transitions and changes in behavior will happen, and that makes a physicist like me very excited. Um, Going and performing environments just by allowing us to change some parameters that are hard to change on the Earth, right, lets us check whether or not our models that we have are sufficiently complete, right? And so having a knob for gravity, for instance, lets us check if we've included gravitational effects correctly in the models that we have developed here on Earth. We have heard these next two we've heard a lot about already this morning, and so they're coming as no surprise to anyone that we want to be doing some research on granular materials, both because this will allow us to improve our interpretations of planetary geomorphology, which leads to solar system science, and also because if the more we understand about the dynamics of granular materials in these environments, the better we're able to create safe conditions and successful missions, right, for whether it's human or robotic exploration and using those resources. All right, next slide, please. So I think it's worth remembering that the way we became experts on granular materials is because all across the surface of the Earth, civilizations, have developed civil engineering practices that work, right, through experimentation, through trial and error, often using in situ material resources, right? So, in Mali, these are more mud-like and clay-like. And they're same in New Mexico. The addition of moisture changed, something from a material that was not cohesive into something that was structurally sound. In ancient Egypt, dragging large objects across the surfaces of sand. How do you modify the material so that you can perform a task that would otherwise be difficult? And what you might be able to see, and I can't move my mouse, but if the person who does can point to the guy pouring oil at the front of the sledge, it turned out that the ancient Egyptians knew to lubricate the grains in order to change the friction of the material, right? And so these small changes of addition of liquids, in fact, can often make a big difference. But importantly, we became experts only at 1G. Our expertise applies to moist 1G environments and not to other environments where we're not expert. And so we should expect some difficulties when we try to carry our knowledge across. All right, next slide, please. So as a physicist, one of the things I'm most interested in is how the many properties of grains, and I've taken these pictures from the Lunar source book as it already come up as recommended reading. It's been really beneficial for me as a physicist to understand how these grains that exist, we know exist on the moon, are really different than the ones we often work with in the lab or on Earth. Right? This would be a very uncommon soil type here on Earth. Okay, so, but as a physicist, how do all these properties of the grain, size, shape, roughness, density, right, what presence or absence of liquids, right, how do those microscopic properties become inherited by macroscopic things like the elastic modulus or the flowability or settling rates that are really needed in engineering contexts? And that yellow arrow is very poorly understood, and that's the kind of understanding you get through careful controlled experiments. Okay, and you can actually see on the right-hand side, I love, this, everyone loves this picture of, a footprint from Apollo 11. It shows that, in fact, these highly structured grains, in fact, can lead to effective cohesion, even though they are very dry. All right, next slide, please. Okay, so I'm going to tell you a bit about the kinds of things that physicists do in idealized situations for which we do not have experiments, and where simply changing the gravity could actually have a really interesting effect. And so these are numerical simulations done on spheres in a vacuum in zero gravity inside a computer by the group of Vincenzo Vitelli. And what you can see on the right is a piston pushing into a set of densely packed grains. Okay, and the yellow is the grains before the impactor moves towards them, and the red is the progression of the shock wave. Okay, and one of the things that we know from these sorts of numerical studies is that the speed of sound is essentially zero in these cases. So uncompressed grains have essentially a speed of sound that is infinite, right? So any sort of motion is going to cause a shock wave to propagate through. Okay, so they have no elastic modulus, right, until you actually start to compress them. Okay, and so whether a packing of grains, okay, is compressed or not by different amounts, that depends on gravity, right? And so if you have lower gravity, you have less compacted grains, okay, you have a lower modulus of rigidity, and you get a slower sound speed, okay? And so basically any perturbation is going to cause a shock wave, right? Now, we're not operating in the singular limit here because we're not working on dry, frictionless round grains, okay? But we're going to be close to that environment in some cases with lower gravity. And so shock waves may be much more common than we are accustomed to in Earth gravity. Right, next slide. These are, again, numerical experiments because it's very tough to do these by the group of Luke Hundich at New Jersey Institute of Technology, and doing something like rheology, so measuring what the response is to some rotation rate, what the velocity profile is inside a simulated granular material. And without going into the details of these results, what you can see is that for the upper left is zero gravity, and then Moon, and then Mars, and then Earth. The important thing to see here is that those curves do not have the same shape, right? And so gravity is affecting the kinds of rheology that you're going to observe when you're manipulating these materials. Right, next slide, please. Okay, so I'll give an example from my own work, which is we have done some low gravity experiments funded by NASA through the READY space tech flights. And so we flew an experiment. Here's Jonathan Kulmer and Tristan and Anna, who are two undergraduate researchers in my lab. And we built an experiment where we looked at what happens when a probe tries to insert itself into a set of simulated grains. So if we go to the next slide, these are not movies, but if someone wants to see them, please contact me. What I'm going to show you here are pictures of a sort of a slice. We can think of this as the surface of the planetary body and into the depth. We're trying to poke into it. Every place you see that's bright is a place that there's more force on those grains. So these are an optically reported measurement. Okay, and what you see is that these patterns of force transmission are quite different depending on the gravity. And what we saw also in that is that it's much more stick-slip behavior stick-slip behavior, so intermittent behavior dominates at higher gravities. And as you go to lower gravities, the motion is much smoother, okay, and much more like a fluid, okay. So understanding that, and there's a big difference between the microgravity, even in the Moon, is a huge difference that we're actually currently exploring in the lab. Next slide, please. Another thing, so if you look at balances of forces, like relative importance of this versus that, we've already heard, so I'm not going to go into this in great detail, that electric forces can become much more relevant in low gravity. Van der Waals forces, which we think of as being small, and microscopic, at the scale of asteroids, are sufficient to provide tensile strength to an asteroid, right? It makes about the tensile strength of a tomato. And so understanding the transitions in which forces we need to account for and which we don't as we move among gravities. And, lunar is the most important for this discussion, okay, but it's part of a general picture. Next slide. Since I'm running out of time, I'm just going to say that I didn't even talk about things like granular segregation, sorting, granular gases, how you establish the stability of things that are like soils, drags on intruders and things like that, all of which are experiments that go on in Earth gravity and have not gone on very much in lower gravity. And those are fundamental questions to be addressed. All right, next one. We're gonna skip this because it's already been talked about. And I'll just say that for me, this ability to do lunar-based experiments, would provide a new place for me to ask basic science questions, in addition to allowing for us to learn things that are needed for the missions themselves. And from there, we can just go to the last slide, which is actually just a repeat of what I showed you earlier. Thanks.